This is Jack Jackson again, and we're going to continue our exploration that we started last video. If you notice, last video we started with a situation where we were given a table of time and velocity, and from this we were able to compute some estimates of distances traveled, of the total distance traveled. We finally got down to this point where we had this table where we added some information to this, and with this table here we were able to come up with some estimates that we call a left estimate, a right estimate, and a t estimate, which was the average of the left and right. And if you recall, what we did on the left estimate was we took this first interval, we assumed the velocity was at the left end of that for the entire interval. We multiplied that velocity by a change in time of half an hour, and we came up with a distance traveled for that first little interval. Then we did the same thing for the next one, and the next one, and so on, and we added those up. That was our left estimate. Similarly, the right estimate, we did estimates on each little sub-interval, but this time we let the height be the right end of the interval, the velocity be the right end of the interval, 53.25, and we multiplied that miles per hour times the elapsed time of delta t as 1/2 an hour to get the distance traveled on that interval, and we did that all the way across. That gave us a right estimate, and we averaged the two. Now we made an assumption that these velocities were increasing as time progressed, left to right here, or progressed from the past to the future, and the velocities were increasing the whole way. Now, in this video we would like to visualize what's happening here. Okay, so the first thing that we want to do is come up with a formula here, and it turns out that I used this particular formula to generate the velocities in that particular table. The formula is v of t equals t squared plus 2t plus 48. So our first task is to make sure that this formula really does generate the table of values that we gave before. And of course we can use our graphing calculator for that. For example, here's a screen from a TI-84. Press y equals, type in the formula, of course x's instead of t's for the calculator, but it'll be x squared plus 2x plus 48. Then we set our table to start at 1 and go up by half automatically. So table setup of the second window, and set it up like that, and then do the table, which is second graph. And here's our table, and you'll see that these values do agree. If you'll scroll down, you'll get the other ones that we had above. So we do see that this formula is consistent with the numbers that I had in the table above. Now with that in mind, let's go ahead and hit graph on our graphing calculator. So let me give you a chance to kind of catch up with me. Go ahead and put this formula in, check this table in your calculator, and then go ahead and graph it. And remember, our time values are going to go from 1 to 5. And so use those for your x-min and x-max. Look at the numbers that are here. I think the highest one was 83. So we could go from really for 51 to 83 for the y's, but we really want to see the x-axis as well. So let's actually just go from 0 to 53 for the y's and graph it. If you do that, you're going to get a window. You're going to get a graph that looks something like this. Now this is a graph using the program Graphmatica. But there's a graph of the velocity curve from time equals 0 to time equals 5. I actually went just slightly into the negatives here, and then up a little bit above. Looks like I went up to 85. Looks like I got this marked down in 5. So it looked like I went from -5 to 85 from y, and from 0 to 5 on x. Y being velocity, x being time, t in hours. So this is really the t-axis horizontally and the v-axis vertically. So there we go, that we have that. So now the question is, how can we go back and see these estimates of distances as something on this graph? How can we visualize that? Well, let's remember what we did. So remember that the first coordinate is a horizontal distance here on the graph, but in reality it represents an elapsed time. So that's our delta t, is a horizontal distance. And our height is, well, here it's a vertical length, a length above distance above the x-axis is our v value, but in reality the v value is a velocity. Now, of course, all the time when we have graphs like this, we oftentimes have something out in reality, and we represent it by x and y coordinates, which are, of course, just locations on the grid, or horizontal and vertical distances from the origin. But in reality, they represent something else. Like in this time, the x-coordinate is the time t in hours, and the y-coordinate is v, is the velocity in miles per hour. So remember, our L1 was to take a change in velocity of 4 hours, which is a horizontal distance from 1 to 5 here, a total of 4 hours. And we assumed that the height was 51, which is the height right here at the left. Well, notice what we ended up doing. We're multiplying a horizontal distance by a vertical distance. Well, that's an area on this graph, an area of a rectangle. So in fact, that boils down to being the area of this rectangle. And so this is what our L1 estimate looks like on the graph. Again, our horizontal distance here is really a change in time, a delta t of 4 hours, and our vertical distance is a velocity at the left end here, our y value here on the curve, and we assume it stayed that velocity all the way across. Now, if instead of going up like this on the velocity, like the formula gives, if it had actually stayed 51 miles per hour for the whole time, then the 204 miles would be correct. But in fact, we know that 204 miles is a little bit small because the actual actual velocity is higher as it goes across. It's sped up. How would we visualize the right estimate then, R1? Well, again, we have one single rectangle that we can do. Again, the base of the rectangle is the full length of 4-hour time span. But this time the height is at the right end of the interval, which was 83 miles per hour. So we see the vertical distance here is 83 miles per hour, or represents 83 miles per hour in reality, and the horizontal distance represents an elapsed time of 4 hours. Multiply those together, we get an area. So areas on this graph are actually distances out in reality with the car. Okay, well, how about L2? In L2, we broke it down into two subintervals, and we did rectangular areas on each one. In other words, we did a distance on each one. In reality, in the graph, that's two rectangular areas. So the first one, we said it was 51 miles per hour high, and delta t is 2 hours wide for the rectangle. So 2 wide and 51 high makes an area here of 102 miles. That was our estimate here, which is the area of this rectangle here. Similarly, this is 2 wide and 63 tall, and we add those two areas together to get a total of 228 miles. That's the estimate we came up with before. Notice that we are finding the height of the rectangle as being the same as the height of the curve, but at the left end of the interval, hence the letter L. For left estimate, the 2 indicates we have two rectangles. Next, we found some more information. We divided it up, and, next we did the right one with still two rectangles. Okay. And we found that it is, again, two rectangles, both of common width of 2 here, meaning 2 hours of elapsed time. And we did the heights a little bit differently this time. Instead of going to the left end of the interval, we went to the right end of the interval. We're still making it a y value on the graph, a v value, a velocity, but it's the one at the right end rather than the left end. So that makes the rectangles actually a little bit taller this time, since this function is increasing, and so this gives us an overestimate of a total of 292 miles. Next, when we looked at our example, we divided it into even more divisions, and we looked at where we actually had 8 rectangles. Here's our left estimate, okay, And if we look at each of these numbers here, we can see that each of these 25.5 miles is the area of this first rectangle. The next one is the 26.625. That's the area of this next one, and so forth. And so each one of those is how many miles we estimated. So for example, this third one here is 28, so we estimated that we went 28 miles on that particular one. That's our left estimate. Since we did the left estimate on all these and add them up, that's our overall left estimate with 8 sub intervals, or 8 rectangles that we added up. So again, we visualize area on this graph is how we visualize what in reality is a distance traveled. Okay, I guess next would be the right with 8 units. In this case, we factored out the 0.05 or 0.5, excuse me, half an hour, and we just added up the height here, which is just basically the same as adding up all the heights and then multiplying by that common width. But anyway, the total at the end, 265.5, is a sum of the areas of all of these rectangles. Now, what do we say we're wanting to do? We're wanting to really take a limit process where we find more and more and more and more and more of these rectangles. Let the number of rectangles in go to infinity, and of course the widths will all go to 0. So here we can see that process kind of going. So first we have 1 rectangle, then we have 2, and here's 4. I'm just going to double it each time, and here's 8. Those are the ones we looked at. And then let me show you a couple more. Here it is with 16 rectangles, and here with 32 rectangles. Just doubling each time. And so, what are we getting closer and closer to? Well, I think you can see that what we're getting closer and closer to is the area where the top of that boundary is our curve, the bottom is the x-axis, and the left and right are these little vertical lines. And so what we're doing is the actual distance traveled, if we could find it exactly, would be equivalent to, or equal numerically to, this area that we see here on the graph. So what we're trying to do here is find the area of this sort of irregular shape. Okay. Now, if this area was something simple like a rectangle or a triangle or even a circle, we have formulas for those things, and we know how to find the areas. Okay, we can use pre-calculus for that. But now we're going to have to apply a limit concept to this. And what we really are doing, again, is breaking it down into rectangular areas, adding up those rectangles, the areas of those rectangles, and then letting the limit as n goes to infinity. And that's going to give us the actual area that we're looking for. And so that is what we're all about here with what's called a definite integral. Okay? So we're going to generalize this in their next video, where it's not necessarily just velocity and time, but any function f of x. Well, how can we see this, and how can we come up with maybe some basic formulas for this? And these left and right estimates are called left and right Riemann sums, and we'll come back to this in our next video.